Today we're going to talk about sampling variability with means and the margin of error and 95% confidence intervals that are attached to those measurements. So by now we've noticed that data vary from sample to sample. Even with data as simple as our bags of M&Ms, very few of us have the same number of M&Ms in our bags. Unfortunately, we don't always have proportion data, or we cannot reasonably collect that data. Fortunately, statisticians like Gossett discovered that if we take many random samples and find the sample means and standard deviations, we can draw reasonable conclusions about the population mean. That's good news, and it shouldn't be a surprise. So yesterday we had proportion information. Tonight we'll have information about means. So for example, we might be curious about the average number of M&Ms we get in a 1.69 ounce bag, the kind that we had in class last week. It's not reasonable to count the M&Ms in every bag, then we'd run out of M&Ms to sell. So we can't get the population data. However, it is reasonable to randomly sample many bags and get the mean number of M&Ms in those bags and then draw conclusions based on our sample. And that's what we did last week, was we randomly sampled many bags. So we'll have two new formulas today. For random samples of size n, the standard deviation, which we call standard error because we don't know enough for it to truly be a standard deviation, there will be error involved. So the standard deviation or standard error of means can be calculated using the formula s over the square root of n, where s is the value of the sample standard deviation and n is the sample size. So let's use our M&M lab data. Now, we can find the mean number of M&Ms in our bag and the standard deviation using our calculator. And I want to remind you how to use your calculators to find means and standard deviations. So you do not have this data on your calculator, so maybe watch carefully and take some notes. But you will remember in class I asked you for how many M&Ms were in your bag and the proportion of oranges. We'll use the orange proportion another time. Today we're going to talk about the average number of M&Ms in a bag. So I have that in a list. And what I want to do is add a calculator page and push menu. We're doing statistics. We're going to calculate some statistics, and it's one variable, just the number of M&Ms. So my variables are in one list. The name of that list, the X list, is total, and I can tab down to OK. And here are my summary statistics. You should have done this in previous classes. So X bar, there is my sample mean of 54.8 or so. And my sample standard deviation is this SX, 1.569. This measure underneath it is the population standard deviation. That's our lowercase Greek letter sigma, which stands for population standard deviation. We're talking about a sample, not all of the M&Ms, just our sample. So sample standard deviation is 1.569. And our sample size, our n value, was 21. I have 21 numbers in that list, so I got data from 21 students. Okay, so that's how you do that on your calculator. Now going back to our new information, there's our mean, our sample standard deviation, and our sample size. We can find our standard error now by plugging in. So our sample standard deviation was 1.569 over the square root of our sample size, 21. And so our samples, our standard deviation, our standard errors of these means is 0.342 or so. Well, what if I handed out more bags of M&Ms and it increased our sample size to 50? We'll assume for now that our sample standard deviation is the same, so the only thing that changes is I'll have the square root of 50 in the bottom of my formula. A quick edit on my calculator page. Changes that to 0.2218 or 0.222. So once again, we should not be surprised that as my sample size increased, the variability, the standard error, decreased. We've been seeing that all along. Okay, next page. So just like with proportions in general, about 95% of the outcomes of a sampling distribution will fall within 2 standard deviations of the mean. Nothing new. And of course, sometimes strange things happen, about 5% of the time. When estimating a population mean, the margin of error can be defined as 2 times the sample standard deviation over the square root of n, or 2 times your standard, 2 times your standard error. And the 95% confidence interval is defined as your sample mean plus or minus that margin of error. So finding margin of error and finding the 95% confidence interval has not changed. It's just now with means we have a new standard deviation formula, and we use the sample mean instead of the sample proportion. So what we're going to have to do in the end is read really carefully. So no surprises here, I hope. After all, math is consistent. So let's do one last example. And this is actually something that happened a few years ago. The Nabisco company claims that there are at least 1,000 chocolate chips in every 18-ounce bag of their Chips Ahoy cookies. An article in a local newspaper reported the efforts of a group of students in their attempt to validate the Nabisco claim. The article reported that the students randomly selected 42 bags of cookies from local grocery stores and counted the number of chocolate chips in the cookies in each bag. The students found the sample mean was 1,261.6 chips, and the sample standard deviation was 117.6 chips. The article stated that the students' data supported the Nabisco company's claim. We want to make sure that's true. So, using those student results, we'll first calculate the margin of error and write a sentence interpreting it in context. So, to find margin of error, we need our sample size, which in this case is 42 bags. We need our sample mean. Not really, we'll do that later, but that's okay. Our sample mean is 1,261.6. And the sample standard deviation is 117.6. So, my margin of error is 2 times that sample standard deviation over the square root of the sample size. So we have 2 times 117.6 over the square root of 42. So my margin of error is about 36.29 chips. So to interpret that in context, we might say that our sample mean is accurate within plus or minus 36.29 chips. So I might have 36.29 less or 36.29 more. Now again, that's in a 95% confidence interval, so we should follow up with that. And that really answers part B. Do you agree that the student data supported the Nabisco company claim? So let's really follow through with that. So our 95% confidence interval, we'll take our sample mean, 1,261.6, and add and subtract our margin of error, 36.29, from it. So our 95% confidence interval is between 1,225.31 and 1,297.89. So Nabisco claims that there are at least 1,000 chips in their bags, and we're 95% confident that there are between 1,225 and 1,298 chips in your bag. So it would certainly seem that this data supports the Nabisco company claim. And that's how you would explain it. So we would say yes, our data suggests that we're 95% confident that there are, on average, because we're talking about means here, between approximately 1,225 and 1,298 chips per bag. And then finally, you're asked to comment on the procedure that the students used to collect their data. Well, what you want to talk about here is sample size, and how did they count them. So the sample size is 42 bags. That's certainly big enough, and we were told that they were randomly selected, and random selection is very important, and so that's good. They told us that in the context of the problem. So we're not too concerned about that procedure. The only procedure you might be worried about is how they counted chips. Did they count just whole chips or partial chips, and what did they consider a whole chip or a partial chip? Because if you've seen Chips Ahoy cookies, they don't seem like very big chips. So this part is okay. We might be curious about how did they count a chip. Like, what is a chip? So anyway, just have a good intelligent conversation about that, and you're all set. And that is it for means, sampling with means, and confidence intervals and margin of error with them. Lots of practice in class tomorrow. Have a great night.